thing. So the mic is on the laptop here.
No, just to start the recording.
Yeah.
Okay. Yes. First of all, thank you, Dr. Glenn, for coming all the way here. Yes, we're so glad to have you today. Yes, I'm pretty sure you've introduced yourself already. Oh,
Actually, I was waiting for the
okay. Yes.
for the beginning, and then yeah, I'll tell everyone who I am, and
Okay.
we'll get going.
Yes. Yep. Yes.
For the
Dr.
slides, I can for the slides I can help going to the next one.
Okay. Yes.
So
Okay.
so,
I mean, I can hit the space bar as easy as the next person too, but we're good either way.
Okay. Yes. For those of you that are online, thank you for coming as well. This is MSU Informs at MSU's first event. Yes. Today, our established speaker is Dr. Glenn Bond from ERDC, specifically in the Information Technology Laboratory. And please enjoy. We will have a seminar as well as Q&A. Thank you.
I want to say a few words about Dr. Glenn. I've been working with Dr. Glenn for some time. Such a wonderful resource. Personally, I get benefited multiple times. I mean, discussing with him, it's always a pleasure. We have been discussing so many things, including AI, travel, to many other things. So, even for my career goals and career plans, I often still talk with him and get his valuable advice. So, he's a great resource, a lot of experience. So, even though it's more like a seminar basis, but you all are welcome to ask anything, like specifically about your career plans. So Dr. Bond, one more time, many thanks for joining us today and for your time today.
It's my pleasure, Dr. Maroof. And Dr. Maroof, I think, needs less career advice than maybe he lets on. But without further ado, my name's Glenn Bond. I currently work for the U.S. Army Engineer Resource and Development Center in Vicksburg. And as was mentioned, specifically for Information Technology Laboratory. So I'm a computer scientist by trade. I have a PhD in computer science, and I taught at that other university in Hattiesburg, Mississippi, that we won't mention in polite company. No, I taught at USM for a few years, and then the offer to move up to ERDC came across my email, and I thought, okay, well, really cool research and all of that. Research that reaches people, and we'll get into a little bit about what ERDC is and what ITL is and other things like that. Originally, going further back in my life, I've worked on aircraft for the Air Force. Love doing that. So everything just kind of fell into place, and making things work with algorithms was a lot like fixing things to me. So that's how I came to be in this. Also, if anyone's interested in this, information will be repeated, but the ITL careers at USACE, which stands for U.S. Army Corps of Engineers, .army.mil, will get you information about careers at ERDC. So, go ahead. Yeah, go ahead. All right, so we've got our basic, and there will be a quiz later. I want to tell you all. All right, I'm gonna make sure you know all the stuff in all of the yellow squares. But really, no, seriously, there's like 4 major commands, or offices, organizations, really under the Army, as far as science and technology enterprise goes. And you're welcome to scan these. the Combat Capabilities Development Command and which is part of Futures Command, Space and Missile Defense Command, those kinds of situations. We're a little unique amongst all of that in that we handle military applications and civil works applications, and even basically wherever there's a pocket full of money and a problem to solve, we're kind of there. So ERDC, as it's called, the Engineer Resource Development Center, has its fingers in a lot of pies, and you can do a lot in terms of a career. For instance, in the 9 years that I've been at ITL, I've been involved with projects that were kind of mundane, that were like, get this data and make it tell us something, right? Have it support decisions. And maybe there's a lot of it. So, put it on a supercomputer. Did I mention that the HPC modernization program has one of their larger assets parked right in Vicksburg at a building I'll show you in a later slide. But so it's a cool place to work. You can see at the bottom here, ERDC is actually comprised of 7 labs, 4 of which are at Vicksburg and 3 are in alternative places. So you've got Golden Regions Research Engineering Laboratory, Construction Engineering Research Laboratory. So the first one I mentioned was in Hanover, New Hampshire. Searle there, Construction Engineering, is in Champaign, Illinois. GRL, Geospace Research Laboratory, that's in Alexandria, Virginia. And then you've got CHL, Coastal Hydraulics Laboratory, ITL, Information Technology, EL, Environmental Laboratory, and then the Geotechnical and Structures Laboratory. All 4 of those are actually established in Vicksburg. So there's all kinds of math about 13% of Army and this and that of the Army S&T budget, but that goes to ERDC, but it ends up being a lot more than that because there are a lot of other pockets that we tap. Anyway, if you go ahead and hit the next slide. So our vision, I'm gonna ask you to write that down later. But these slides are helpful. They'll let you dive in as far as you want to, but you can see where the different labs are. And then there are other places like up in Alaska, there's a research location where they're researching permafrost. There are places where they research wetlands, and there's a place they go to blow things up, because we are the Army after all. And some of the same kind of research protects people against being blown up. And some of that research helps protect people against natural disaster and provides resilience for utilities and structures and all kinds of situations like that. And underneath it all, you'll find that most all of it is going to require some form of computing. Like I was discussing with Todd about aviation applications and things like that, because you think, well, aerospace engineering, that's about designing airplanes. Sure. What about simulating your designs before you go manufacturing them, or any number of other issues? As lots of just trying to get information out of data that's going to inform how you design things, or how the next generation is going to work, or how about additive manufacturing, or corrosion resistance, or, I mean, the list goes on and on and on about how you could inform design, trade space, or other kinds of issues. So we've got a lot of work that goes on for designing things and keeping things moving, keeping people safe from Mississippi River flooding, keeping harbors open, keeping European carp out of the Great Lakes. I mean, the list is tremendous. Show of hands, who would have thought that carbon fiber reinforced plastics with a particular rosin would be stronger than welding when we're talking about a massive gate that diverts flow on Mississippi River? Would anyone have thought that? But the guy, there's a guy I work with who's a civil engineer who came up with that idea, and it's working, and they can apply these patches underwater. They don't have to, you know, I mean, it's crazy cool because this thing flexes better than a weld and actually will stay on better. There's a seat, I think, right over here. So, I mean, they're just, you know, that you name it, and I'll talk a little more about some of the solutions I've worked on, or and you don't necessarily have to work for ERDC to get into some of this. Ask Dr. Maroof. He's been involved with some of this, doing, you know, on a research level and collaboration level, and you know, you can be you know, one of those clever people who writes grants for the broad area agreement, things like that. There's just go ahead. Just a ton of ways to be involved. So ERDC was actually established in 1999, but well before that, let's see, I think it was Coastal and Hydraulics Lab what was to become Coastal and Hydraulics Lab was established all the way back in 1929 because of a huge flood that happened then. There are similar stories. During World War II, there were these, it's a portable floating harbor that was designed in Vicksburg. Super, super secret, hush hush stuff, but it's part of what made D-Day and Normandy possible. There's a slew of things here. The Arctic research that started in 61 that began the CREL, we call it, Cold Regions Research Engineering Lab, and so on, right? My personal favorite here, the supercomputers and the origin of ITL, because I, you know, like working on big iron, we call it. So imagine, has anybody got an idea what a supercomputer actually is? The nuts and bolts, go ahead.
Like a lot of computers linked together so that they can do a lot of computations.
Yeah, very good. Very good. So imagine, everybody's seen a dual motherboard, right? Maybe, you know, 2 processors on it, lots of memory, maybe 128 gig, maybe 256 gig, something like that for a standard node. And large memory nodes could be, you know, like 750 or higher gig worth of RAM and a couple of processors. So you got maybe 44 cores or something like that on a board. Now imagine linking that with several thousand others just like it. And in order to get these things to talk to each other in a way that we're not here until, you know, sometime in the next decade, we use super fast networking to get them to talk with one another. And it used to be that we had to use, and it's still done some, MPI, message passing interface, in order to write programs that would say, okay, I'm taking care of this little piece of this geographic area, but what about the borders? Oh man, what happens right here affects what happens right over the fence. Oh, I got to tell that processor over there, pass the message, right? And that processor's, on the other side of the fence, got to pass messages back, and there's messages all over the place trying to get. I mean, there's the embarrassingly parallel stuff. Like I have 10 million files that I've got to affect computation on this way, and the results stored locally. And there's, so I can send each of those files out to a different process, and it's done. Or there's stuff like I've been describing just now where we've got to pass all the messages. But supercomputers are huge on that, and we're always trying to move forward and forward and forward. So the newest one is Carpenter, and there's a slide about that later, and I'll talk a little more about it. But we've got a fairly deep history running through the 20th century and into the 21st. So while ERDC was established in '99, there's a lot more to it, and lots of old black and white pictures of people doing really cool stuff from history. Anyway, next slide. So you might ask who we are. And so our age distribution, you can see, we're you guys. We're not me. I'm okay, quit. I see you there. So I'm in Gen X, right? Just barely. I'm all the way to the right-hand side of Gen X. I was born in '65. So you can see I'm off over there on that tail end, just to the left of the baby boomers and all of that. And then you can see Gen X, the rest of Gen X is some, but huge component of millennials. And they say Gen 9/11, however you want to, Gen Z. Lots of young folks comprising the engineers and scientists, that's ENS, admin people, technical people, are all, well represented with us. And then there's a breakdown to the right of career fields and such for those who are terribly interested in it. I understand we're being recorded, and you can come back to this if you really need to, and I'll answer some questions about it. But yeah, we've got a little bit of everybody you can see here that you'd want to refer to answer a technical question. We even have librarians. We have an established ERDC library that's actually part of ITL. Anyway, next slide. So the header kind of says it all. Premier R&D facilities. And like I mentioned before, we have places where we go to blow things up and test how that works. We have places where we go to put waves in a pool to see how they're going to affect structures, like you might park on a beach somewhere. What they call the littoral zone. Has anyone heard that term? It means basically a beach area, where water meets and all that. So say a floating pier. We want to know how much can it withstand a structure like this. So we build a small model and put it in a pool. And then somebody gets the bright idea, hey, for cheaper than that, we could run zillions of simulations if we could just get all those rules into a computer, right? So people dream up all sorts of ways for this to happen. So we've got the DoD Supercomputing Resource Center. You can see this couple of buildings just went up on the ITL campus. And then across the street from them, in the area where we're just going to decommission Onyx, which only went up about 4 years ago. We've got Carpenter, a brand new supercomputer. And so we used to name our supercomputers after gems, and now we've come up with the idea to name them after Congressional Medal of Honor winners. So Kyle Carpenter, I had a chance to listen to the young man talk, and he basically won the CMH for throwing himself on a grenade to protect his friend and fellow Marine in Afghanistan, and lived to tell the tale, and is quite the speaker. He's mid-30ish now, and came to the dedication ceremony. But some of the other pictures that we've got here, the blast load simulator, right? We're always trying to test how to resist being blown up or how to blow things up better, right? There's always somebody doing research like that. But what about, see the robot in the very middle? Well, it's not an obvious robot, is it? The 8-wheeled vehicle that's controlled robotically. So we have infrastructure all over the United States that's aging and failing, and in particular, lots of dams. And many of these dams have tunnels going up to a gate in the dam, and it's, as you can imagine, a fairly treacherous thing to send a human being up there to inspect the dam and inspect that gate. Okay, and this thing is actually capable of doing that for us. It also goes into like GPS denied areas and makes maps. It goes in and makes terrain maps and things like LiDAR maps that you could say compare a before and after for erosion or things, you know, all kinds of applications like that. Let's see, cognitive ecology and ecohydraulics research. I honestly don't know anything about that, so I'm gonna just pass on that. New heavy vehicle simulator. You can see if you study the picture close enough, it's a behemoth vehicle, and I don't know much more than that about it. But you know, there's all kinds of situations where, again, if you have an answer, if you have a question, you know, we've probably got a way to find an answer. Next slide, please. And so it attracts people like those of us in this room, right? You know, these kinds of situations. I mean, this is hopefully why you guys are studying the things you're studying. Yes. I mean, who here is not curious? Raise your hand if you are not a curious person. You know what I was going to ask you if anyone raised their hand? Why are you studying what you're studying? Right? So that's what we're about, delivering solutions right there. And here's a lot of the areas across which we do this. And we're not limited to these things, but these are a lot of our main thrust areas, like civil works, like I was telling you about with the dams, or the CARP, or the same engineer I was telling you about that figured out about the replacing the welds with the carbon fiber reinforced plastics. He and another engineer did a study on simulating paddlefish that bill. It's a very unique structure. So trying to create something that's manufactured that emulates those qualities, because it'd be very useful in terms of a material to use to build all kinds of things with. Engineered resilience systems, where we do all kinds of work with trade space analysis, or has anyone heard the term physics-informed machine learning? Yeah, cool. So PIML, or physics-informed machine learning, where we use physical constraints to, you guys know what a loss function is in ML? So you use physical constraints in your loss function. So you use physics, instead of just saying, I've got this little test, use actual physics, real world physics, to sharpen your machine learning as it goes through iterations to find your solution, right? And just tons of other things. Part of ERS, I worked on ERS to do curate and draw answers from to provide rapid decision-making ability for ground vehicles with predictive algorithms. So there was all kinds of stuff downloaded from what's called the CAN bus, the collective area, something or other, collective area network. There's another N there, and no, it is just CAN, I think. Anyway, it's like things like your anti-lock brakes and your transmission and your engine all have leads that go into the CAN bus. And it's the kind of thing that puts up the yellow light and the red warning light on your car. But these are on heavy vehicles, and they were collecting all that data, and we were using it to predict when things were going to go wrong, predict faults and failures, right? So, hey, you don't want to use that vehicle. You want to use the next one over to work on this machine. And by the way, that one's going to fail in so many hours, and it's going to need this part. So let's get a jump before it fails and order the part so that it has less downtime. So effectively, if we had 1,000 vehicles and we have an 80% readiness rating, that means we effectively have 800 vehicles at any given time. If we can raise that readiness rate, say 10%, now we got 900 effective vehicles at any given time, right? That's a simplified version, but that's essentially what we're talking about, right? This is ERS. There's so much more to it. Geospatial research covers all kinds of issues with how do we get, say, across a particular area, maybe what kind of vehicle is it going to take? What kind of bridge is it going to take to get across this river? Things like this. What kind of terrain can we expect when we're there? You name it, right? Installation and operational environments. We're talking about like how to build more resilient, smarter, cheaper ways to house our military. And these kinds of things will bleed out into society at large in terms of how we build, maybe next to wetlands or something, next to as opposed to on, and how not to, to have them succumb to hurricanes so badly. Military engineering, well, again, we like to blow things up, don't we? But there's a lot more to it than that. How do we stay resilient in that area? Anyway, next slide. Oh my goodness, I'm sorry. That's my wife. She knows better than to. Okay, so we have just a zillion partners, and I'm just going to let you guys look at this for a moment, but you can see government. There's, features. Army works with Air Force and Navy and vice versa, and NASA and all that. Academia, you can see Maine, Mizzou, Arkansas, Virginia, Texas A&M, Hines Community College, and of course, MSU. There are just, tons of academic partners and industry partners, Raytheon, Lockheed Martin, Boeing. Used to have a regular call on a project I worked on to do predictive models on CH-47s, the D model, the Chinooks. They're really cool. They're the one with they look like a trailer house supported between two main rotors, built all the way back in the 60s. Amazing aircraft. Let's see. International partners. kind of speaks for itself. A friend of mine just spent a year in London on a TDY, just to go and work on a developmental assignment over there. Okay, so next slide. So ITL, this is us. This is me, right? We've got several different areas here of main research, but we do things like supercomputing solutions. We do things like computational science and engineering. So you see sensors, data analytics, systems engineering, digital twinning. How do we wring the answers from the data? How do we figure out how to put this or that, build it into the computer so that we can run zillions of simulations cheap to find out the things we need to know? Or how do we, say, develop a sensor network where we can feed information that we gather from an asset through maybe a neural net, maybe a predictive model, whatever, but to give us an answer that we need, that it would have taken us a month to get before, and now we can get it in a day or less, so that we can get it in time to do something with that information. Decision support, right? And sometimes that involves supercomputing because it takes a lot to train some of these models where maybe we can then kick them out to edge computing and things like that. So we research edge computers. We do work on supercomputers. We sometimes just work on our desktops, right? I used to be a C programmer. Anybody remember C? Anybody code C? You code C? Yeah? Okay, so my wife, though, would tell me that coding C is like going out to the barn and hitching up the horse to the wagon so you could go to town. And she said, by the time you get the horse hitched up, I went out to the Porsche and put in the key, turned it, and I'm already there shopping, right? Because of all the issues like, things like TensorFlow, RStudio, all the package-based programming and things like that. So it's important to know what's underneath too, so you can get a handle on this whole clock. Maybe not the cyber folks, they're a little different, but they're no less important. As we can see with everything going on lately with the AI spoofing and all of the craziness or encrypting data and holding it hostage and all of that. Just you name it. But we've got if cyber's your thing, we've got an award-winning red team also, right? So ITL is it's like everything computing. There's just a lot there to do. There are areas we don't go into that I think we should, but they're few and far between. There's just a lot that you can find. And the great part is, if you're someone studying to be the kind of people you're studying to be, you can make the choices to get involved with the projects to get yourself, where you want to be as far as working on something interesting. It's pretty much that simple. I mean, yeah, you're going to be tasked to maybe do something once in a while that you're like, oh, okay. But by and large, you get to do a lot of what interests you, right? Next, please. Again, you see our workforce is very much shifted to the left. Young people apparently rock at ITL and ERDC. Okay, and here you can see to the right the list of, that's a partial list. But I work with, just in my branch, let's see, there's a physicist, several mathematicians, civil engineers, structural engineers, aerospace engineers, lots of computer scientists. I work for computational analysis branch. So, and there's a whole branch dedicated to systems engineering. We actually have, we call ours ICER as well. I don't know, you guys familiar with Mississippi State ICER? At least some of you, but yeah, and Mississippi State ICER does work with us as well. So yeah, lots of places. So we've got like 400 people, and I think it was right at 2,500 at ERDC overall, like 74 duty stations other than Vicksburg. Mostly it's going to be the four I mentioned though: Vicksburg, Champaign, Hanover, and Alexandria, right? Anyway, next. Premier facilities, right? And I've kind of talked about some of this. Don't worry about networks. That's all, you know, different networks that are supported to get things done. Does anybody have any experience working with military? Okay, so in lots of places, military networks are very locked down, and I'm not saying that we're not, but if you are on that top bullet there, Defense Research Engineering Network, DREN, you get a lot more leeway to administer your own machine. Now, there's trade-off. You have to, you know, basically sign lots of paperwork that says you're going to comply with the overall rules and that you know what you're doing. But you get a lot more leeway because you'll need it to do the research you're doing, right? Let's see. Supercomputing infrastructure. Yeah, we have an impressive amount of raised floor, you know, cooled area for the supercomputers, chilled water plants, all that. You can see here's our overall facility. Just real quick, and I'll speak up so the mic can hear me. And I don't think you can see me, but in the upper right of the image is the building where I work. Although I do a lot of my work from home. Down here at the bottom of the image is the supercomputing center, those two buildings. The newest ITL building is the one to the right here, which is where the lab director and lots of our newer real estate and office spaces. And then there's other like cooling tower and such off to the left of that, and backup power and all kinds of other issues. But that's our main facility. And it's kind of set back away from Vicksburg, which if you've ever been there, it's not really big. Go ahead, please. So I keep mentioning HPCMP, High Performance Computing Modernization Program. It's spread out across like Air Force, Army, Navy, you know, the Army Research Lab, Air Force Research Lab, us. There are a bunch of different computers. And there are all kinds of people doing work on them, not just military people, but academics too. You can get access, and you know, if you're working on the right project, we'll basically send you a YubiKey that gives you access, and you can get secured access to and get into it. And there are all kinds of computationally supportive software available, you know, and a lot of that's machine dependent and that sort of thing. But yeah, it's a really great resource. So the red area says what? DoD-wide program, national asset, provides the, you know, the capabilities and expertise. to solve critical mission challenges, right? Whatever they decide that is. All right, so next slide, please. Because I sense we're running out of cyber. Is anybody here working in any kind of cybersecurity beyond just, you know, making sure that you're not using the same password for everything and it's not your pet ferret's birthday?
Then I'm sure the cybersecurity class that.
Well, I know that's good. It's good to take an active interest. That's excellent. And you know, anybody who's awake realizes it's pretty important. Yes.
Masters from University of Maryland Global Campus and Cybersecurity.
Nice. Okay. Want a job?
Yes, sir.
Do you really? Okay.
Yes.
Well, there will, in fact, the last slide's going to give you all a way to get in touch with ERDC and ITL.
Thank you.
Oh, no sweat. Not at all. Thank you for coming. All right. So we've got, I am more of a tangentially involved. I'm the person who learns what I need to know to protect myself and the things that work, you know, that make sure I follow the rules, but to dive into it deep, that's a whole other issue. As far as protecting systems and being the kind of person to make policy, that's a whole other issue. And these folks do it, and they do all kinds of research about it. And they do the real world work to watch the traffic and keep all of our systems safe. So that's a whole area of focus with ongoing funding and all of that at ITL. So I would get further into those columns, but I'm not as qualified for that. Go ahead. So this is more me. You know, I've done, like I said, a lot of work with data and computational stuff. I did some work with physics-informed machine learning. Did some work with, they call it tactical HPC here, basically edge computing. The idea, if you're going to say, set up a system of predictive models and logistics chain and things like that to support a system in the field, training the models takes a lot more computational horsepower. So you do that, say, on HPC, and then send the models out to run where the data is going to be collected. So if I'm off in some Waristan and I offload data off of an airframe or a ground vehicle or something like that, and I have tactical HPC there that can run the model on that data, I get the answer right then and there. I don't have to transmit it all the way back. I get the answer right then and there that I need. And I say, oh, you're going to fail in 2 weeks or 2 days or whatever. I better get a part ordered like yesterday, right? Because again, I've got logistics issues. So what's the best way to do that? Well, my tactical HPC says, all right, here's the best thing I can do to get the part here as quickly as possible. And, you know, and we initiate that again, get, you know, to raise our readiness, right? If you have 1,000 vehicles and an 80% readiness rating, you effectively have 800. If you can raise it to 90%, you effectively have 900 vehicles. Like I was saying earlier, does that make sense to everyone? Because if it's not ready, you might as well not have it. Right. So cloud computing, that's I don't know nearly as much about that as I'd like to. Just haven't had time doing lots of other things that I do. Anyway, next. Again, this is more me, data science and engineering. So collecting the kinds of models that so if you look at does anybody know what the top helicopter is on the right? Very ubiquitous across the armed services. Air Force has the Pave Hawk, Navy has the Seahawk, Army has the Black Hawk, Coast Guard flies them, all of that, right? The Black Hawk, the H-60, right? So they've been flying these since I think the late 80s. And sometime in the late 90s or early 2000s, they stuck vibration sensors on them to collect even more data than they already were collecting, and that sort of thing. But bottom line, we would say work on something like this to tell us, should we tear down this transmission in order to replace this filter, or should we, how do we know about this or that? How do we know about all kinds of things? There are just a zillion things that can go wrong with a helicopter, because they're very complex, and lots of ways that you can use data to predict things about that. So we study things like the Black Hawk, one, to inform how to operate it better, but two, now we're looking at, say, what's going on the bottom here. Now that's not an actual design. Oops. Something like there are 2 or 3 of them now that you guys may have seen in the news, FLARA and FARA and all that, that are just crazy awesome, fly a couple hundred miles an hour, coaxial main rotors, pusher props, all that kind of stuff. Super duper performers. But studying Black Hawk can inform us about how to build the next generation, right? What worked on Black Hawk, what didn't work, and what performs and what doesn't, and how do we tip that into the better area. Even studying like mundane big diesel trucks. And you say, well, the next generation is going to be electric. Well, sure, well, still have wheels, still have a lot of the same components, right? But anyway, off we go. There's just a lot to be done to support decision making across the board everywhere to get things done smarter, faster, cheaper, right? So acquisition, mission engineering, really a lot more of the same. How do we say get people to work better with computers? Raise your hand if you never worked with a computer. Right, pretty good bet in this room that that's going to be a 0, right? But raise your hand if you never thought maybe there's a better way, right, to get something done. In fact, as I was getting ready this morning watching, has anybody seen the new Apple headset, the AR headset? And there was a review of that and some of the kinks with it, like if you're typing, having to look down or else you lose focus on the virtual keyboard, and this, that, and the other. And I mean, it's really cool stuff, but there are kinks to be worked out, right? Mm-hmm. More than that, though, what are computers good at? Are they smart? People are smart. Computers are dumb. Computers add and computers remember, but they're not smart in the sense people are. They can't make intuitive leaps, can they? And so how do you put the two together to get the job done better than either could do alone? Or how do you optimize that mix, right? How do you put together something as complex as sending a group of aircraft halfway around the world to perform some task, with all of the supporting stuff that goes behind it? how do you know that when you get to someplace that the sand is gonna be a problem for joints that need to be lubricated, or combustion cans where the sand becomes glass, and, you know, you name it, man, there's just so much behind all of it. You know, it's beyond just hauling enough steaks and bottled water to keep the mechanics and the pilots and the other air crew and supporting staff happy and fed and all of that, right? It's much more than that. It's how to get them overland or through the air, or it's, you know, anything else like that. So these are, you know, some real world issues, right? Modeling and simulation can get us a long way. Anyway, go ahead and yeah, slide 17 there. Okay, so with that, I will take questions. I don't know, how are we fixed for time? I ran over, didn't I?
I have a quick question.
Sure.
Have you done any projects additive manufacturing related?
I have not, but I know a couple of people who have, and there are some ongoing projects. Have you heard about the ginormous boat they're building? I can't remember. It's like 80 feet at University of Maine. I think it's 80 feet. It's big.
Somewhat, yes.
It's the cross section of it is what's the limiting factor, is my understanding. But yeah, there's all kinds of quality control involved with that. You know, with and you know, what I mean by that is assessing that everything's going right with the AM as you're doing the building. Yeah, it's the next new thing, man. You know, when you're halfway around the world and you can build a part instead of ordering it from the other half of the world, man, there's just nothing like that, right? So yeah, so I haven't been personally involved with them, but I know of them.
The follow-up is do you know what kind of material they're doing with? Is it metal based?
Some of it is, and but of course, much more of it is the plastics based. I think there may even be some CFRP element to it. I'm not exactly sure how it works.
Oh, thank you.
Oh, no sweat. Anybody else got questions? I'll answer questions as many as you need.
Thank you, great seminar.
Oh, sure.
To get a job as a researcher, let's say at NASA or this kind of laboratories, what you think is the best important factor in the CV to consider? Or what's the best general path starting from PhD?
Well, first of all, be that person who is a problem solver. So have your CV reflect that you know that you are good and skilled at solving problems. For instance, do you know how many of us have worked with machine learning? Show of hands. All right, keep your hand up if you know what stochastic gradient descent is. Yeah. So, okay. Good. Do we know it in terms of ML? Or do we know it in terms of our, you know, linear algebra and advanced calculus?
So I'm still trying to understand the math.
Oh, everyone is.
Right.
It's like quantum physics, right? Yeah, go ahead, put your hands down. So this is my long-winded way of saying, if you're the person who's curious enough to go find this stuff out, I think it's probably going to find its way into your CV. But also don't shirk from the writing. How many of us are published?
I'm working on it.
Good answer. All right, good. Good. How many of us are or would be working on it, or what if we could? Find the opportunity. Get your feet wet. Okay. How many of us know, how many of us have ever heard the term standing on the shoulders of giants? Right? Do we know what it refers to? All right. What's it refer to?
It's, you just, it was Isaac Newton, right? He said, if I have seen further, it's because I've stood on the shoulders of giants. And he was saying
That's
it was built on all this stuff that other people before him found out.
that's what I've always understood to me too, not the REM song. I read something that said that someone said it before Newton. Doesn't matter. The concept's the same. That Newton, clearly was visionary, but he didn't get where he got alone. He had to use Copernicus, Galileo, this sort of thing, right? So when you're standing on the shoulders of giants, you're reading. Yeah, how many of us regularly read research? Or when we're curious about a solution, do we go read what's someone else done about it? Yeah, because if not, the other thing you're doing is reinventing the wheel, yeah? Do we really want to reinvent the wheel? I know I don't. And I've been guilty of it, I can tell you from experience. So that's what also needs to come out in your resume. So get all the chances, take all the opportunities you can to research with smart people like Dr. Maroof.
Well, that's certainly not true. We don't know that,
What?
but that probably is not true.
That probably is true. Take every opportunity you can to get with the, does anybody know Dr. Bouchon? Yeah, I mean, if you can find work with him, with Dr. Maroof, and there are lots of people. Does anybody know Dr. Rahimi? You all do. Good. Listen to this guy. If he ever says something, listen. Right? Don't say, oh, that's for other people. No, okay. He knows of what he speaks. In fact, my wife was his graduate advisor. But get in with the kind of people who can teach you how to research, how to answer questions. Get in with the kind of people who can teach you how to read effectively, how to do a literature review, and how to publish. Now, you don't have to. How many of us are in search of our 4-year degree? Show of hands. Okay, and you don't necessarily need to be involved at that area. Okay, but at that level, when you're just coming in with a baccalaureate degree. But if you're coming in with a graduate degree, it's good to have the idea that you're going to go in that direction. Okay, or that you have and you don't have to have a publication per se, or 2 or 3 or whatever. You just need to be of the mindset that you could do it and that you're curious enough to do it, and that you're willing to get your feet wet in that area. The only people that I work with that don't do that or on the right end of that demographic curve, and they say, oh, just take the 2 on your performance report, right? It means just let it go and be, and they're the crusty people, and they're on their way up. If you want to be the person who gets the job and moves into a position of responsibility and does fulfilling work, that's part of it now. That's part of it. So be the person who can answer questions. Maybe not off the top of your head, but answer questions, solve problems, get involved with research. Did that answer your question?
Yeah, thank you.
Okay, good.
And to that end, there are internships that are also part of.
Yes. Yeah, one just crossed my email. Now it was for like sons, daughters, and relatives of ERDC people, but there are also, gosh, trying to remember the name of it now. You have my email. Jog my memory and send me an email that says, hey, what was the scholarship you were trying to remember? And I'll get it back to you so you can share it with them. But yeah, there are certainly internships for people at all levels to become involved and work as interns. Pays not as good as, but it's not bad. And it'll get your foot in the door. There are a lot of people. I know a guy right now who's running a major program, who's been at ERDC for about 10 years and started out as an intern. It's what you're going to make of it. Other questions?
Recommend you all try the internship. Our IC department, that several of our graduates also worked as an intern there. So, it's a very rich experience when they work. Some of the things that you can get a chance to work, which often in university you do not get the chance. If you want to go get into our HPC, sometimes it's challenging even to get to there. Not every student get a chance, but resource-wise, you can get a lot of things. And of course, the people who will be there are very supportive, research-minded. So it's a very different environment. I would recommend you all try. I think I know one program, the high performance computing moderation program. I think there are some internship opportunities, and Dr. Blaine also previously shared some internships, other positions too.
And there should be information about that also. If you follow that lower QR code to the ERDC live stream and the ERDC social media, there should be information there as well. But yes, HPCMP and ERDC in general both have internships available, and multiple internships. So my advice also would be, when you're applying, be honest about your interests, because if it interests you, isn't it easier to study? It's easier to work too, what you're interested in. So, be honest about what it is that you're interested in. Don't expect that you're going to get a job doing computational fluid dynamics if you're interested in, if your main interest is authoring video games. Although there may be, there are people working with, it's Real or Real 2, something like that. Does that sound like it's a rendering engine, commonly used with, in video game authorship, but it's being used for other issues with virtual reality and with virtual environments and digital twinning. We have a whole media lab with, the folks in 3D goggles. I think you saw an image upstream from this of somebody working with that. But yeah,
Is it Unreal Engine?
it probably is. Yeah.
Unreal Engine 4.
Unreal should be, yeah. And there was at least one other. I want to say Quick, but that may be ancient.
Because Unity. Not Unity.
Unity, and that's another possibility. And they probably are using Unity and Unreal. I know Unreal, probably using Unity and possibly even a version of Quake that's newer than we know or something. I don't know. But there are all kinds of, imagine putting on the AR goggles and they're showing you what you're working on. And you point at a bolt and it says that needs a 12 millimeter, wrench is what you're going to need to loosen it or whatever. Or maybe you look at the whole figure and it shows in the upper area an exploded view of it, or something like that. Or maybe there's another window that says, that has the data from this vehicle and says most probably the problem is with this filter or this valve or whatever, and shows you exactly where it's at. And then maybe somewhere else there's something that you can pull in that's the technical manual on how to remove and reinstall this component. All kinds of things like that are coming into possibility, coming into their own. Right? There's the speculation goes on forever and ever, right? Anybody else got a question? Talked you all out, didn't I? It's my pleasure to be here. Thank you. All right. Oh, no, thanks. I'm gonna go ahead and get pointed home because it's gonna be 7 before I get there.
Thanks everyone for coming to the event. Feel free to grab the breaks and pizza on the way out.
Sir,
Coffee for you, or
have you got coffee somewhere?
I need to get to the Starbucks, which maybe 5 minutes.
I'm happy to accompany you to Starbucks and grab a cup.